I'm Sarah, as Keelan said. She sums it up fairly well there, so I'll just jump straight into the presentation. So I'll start right from the beginning. Back in 2011, I was 9 years old, and my dad, who's here, first brought me to Cork Dojo. And around the same time, he got his first iPhone that had Siri on it. And I started playing around with Siri, and this was my first encounter ever with a chatbot. And I thought it was the best thing since sliced plant. Like, I'd never been able to talk to a phone before. Like, that is so cool. So when he asked me what I wanted to do for my first Python project, which I was learning in Cork Dojo at the time, I said, I want to build Siri. And I kind of did. I built this procedural bot called Leela. So this is just a snippet of code. So she wasn't actually artificially intelligent in any way. She couldn't learn. She just she could only answer pre-programmed questions. So if she was asked a question that I hadn't programmed in already, she would just give a little smart aleck answer, like I had there, smart answers such as that's a silly question and things like that. She couldn't actually cope with things that she didn't already know. But after that then, I put her aside for a while, and as Keelan said, I worked on a few other projects until I came back to her in 2016 with the rest of my dojo because we were looking for something to take to Dublin. And I was tasked with research and design of Leela 2.0. And my first thought was, okay, we can't possibly program in every single question and answer in the English language because that's just, too much work. So I said, okay, we need to be able to teach this girl language somehow. And I started researching. And that was how I came across the absolute mess that is machine learning. For Dublin with the dojo, I didn't actually get around to adding any artificial intelligence. We just got around to adding means function, which is the closest I got without actually touching on neural networks. So basically, if you typed in Sarah means awesome, and then later typed in Sarah, she'd come back with awesome. But I could see Young Scientist just around the corner, and I wanted to see what this whole neural network scenario was about. I didn't know anything about it, so I dove straight into it and found this. Oh my god, what? I had no idea what was going on. I attended one of these AI meetups actually, and I just remember coming out even more confused than I went in. I just had no idea what was going on. So I started out with a TensorFlow tutorial for a translation model. Now, I know that what I took to Young Scientist was a chatbot, but in fact, I found out that a neural network for translating between languages would work just as well for a chatbot, because all a chatbot does is translate from question to answer. So I was like, perfect, this is going to do, because this particular tutorial had really, really good instructions on it, really clear instructions. So I ended up using that. And I also had to make 1,000 questions and answers by hand. It's as tedious as it sounds. And I wrote a program, just a procedural program for cleansing and tokenizing the vocabulary in it. So in the questions, I stripped out capitals, punctuation. For both questions and answers, I programmed in synonyms. So I said, for example, like Second World War, World War II, things like that. There's loads of different ways of saying the Second World War. The bot had to figure out that they were all the same thing. And this reduced the vocabulary of the chatbot. So because, you see, Alan, that's what I named my chatbot, he processes strings of numbers, not words. So the less numbers he had to cope with, the easier it would be. And Alan is actually named after the founder of computer science, Alan Turing. And so I took Alan Turing to the Young Scientist 2017, and as you can see, we won a display award. It was kind of bad. He didn't really work, but I was proud of him. I thought it was cool. He got questions right sometimes. I mean, it was great. But, considering that I only had 1,000 questions and answers and the optimum is 6 million, the fact that he got anything right at all was actually amazing. And to quote Andres Karpathy, neural networks are unreasonably effective. But then I realized that I had no idea what a neural network was. I literally just took this tutorial and just ran a few lines of code and bam, here it was. But what had I actually done? So I took a few months. This is what I've been up to since January, to just try and figure out what's actually going on in the background. So how does AI actually work? But to actually figure out how AI works, you've got to go right back to the history of AI. So back in the 1950s, so this is the first computer here, ENIAC. Back in the 1950s, when they first developed ENIAC, they were saying, well, you know, brains do computation, computers do computation. Why are they so different? On the face of it, they do different things. Computers work in recipes and procedures like Lena did. You know, do this, then that, then that, then that. If this happens, do this. Whereas brains are better at things like intuition and forming their own opinions and extrapolating from incomplete data. Computers kind of get a bit muddled with that. So they said, why is that? And on the face of it, it's because the architecture of brains and computers are hugely different. So brains are made up of neurons, brain cells, and you have 100 billion of these just in your brain, and 30 billion in your prefrontal cortex alone, which is the outside part of your brain, and that's responsible for things like language and consciousness, and it's the most human part of the brain actually, is what they say, because humans have the biggest prefrontal cortex of any animal. Okay, so then they were like, okay, so this is what a brain is. Why don't we try and turn this into a computer and see if it simulates a brain? And that's how they came up with the perceptron. So the perceptron is a mathematical equivalent of a neuron, a brain cell, and this is a diagram of a perceptron. And I feel like the best way to explain how the perceptron works is actually just to go right back to the most basic mathematics of it. And in fact, I did these maths back in second year. So my second year maths teacher was Miss Bean. And little did she know when she was teaching us linear algebra that she was actually teaching us about the inner workings of a perceptron. So this is actually so easy. It was second year math. This is just a line on Cartesian coordinates. It can be notated as y equals mx plus b, where b is the offset, the y-intercept, and m is the slope of the line. It is so simple, and m can also be notated as delta y over delta x. It's cinch. The best way I can explain how this applies to neural networks and perceptrons is with the use case of a car journey. So if you think about a car journey, okay, start from the start. It takes you a few minutes to get into your car and, you know, put on your seatbelt and start the car and back out of your driveway. So already you've like a minute or two added onto your journey. In this case, that would be B, the offset. So you already have a few minutes before you've even started moving. And after that, obviously the faster you're going, the less time is taken. And the longer you're going, the farther the distance, the greater the time. So you can actually say that in the same way as y equals mx plus b, where time equals speed by distance plus the offset. So if you want to make this into a perceptron, all you have to do is input the distance here with x. M and b will actually be worked out during training. This is sigma, so just add everything up, and out comes the time. And then if you want, you can add you can make it a classifier to figure out whether the journey was fast or slow, just by adding an activation function, which I'll explain later. And there are a few different activation functions you can choose from as well. So this is the same diagram of perceptron I showed you earlier, except this time you can have as many inputs as you want. You don't just have to have one, you can have as many as you like. But that would mean that then, you know, we had like a two-dimensional graph there. If you have more inputs, you have multi-dimensional graphs. So from this, you can say that a perceptron splits a hypercube of n+1 dimensions by a hyperplane of n dimensions. And that's it. So in summary, the gate is to the computer as the neuron is to the brain, as the perceptron is to the neural network. And that's it. But the thing is, perceptrons aren't actually all that useful on their own. I mean, splitting hypercubes with hyperplanes is a very, very small subset of problems. Take, for example, this plot here. It's actually a classifier for handwritten digits, 0 to 9. A perceptron alone could not do this because it's just too complicated. So they actually stopped research on perceptrons for a while, but then someone said, hold on, we don't just have one neuron, we have loads of them stacked up in layers, so why don't we put these perceptrons in layers? That was what I was just saying. And it actually reminded me of, the scene from Shrek, where Shrek is explaining to Donkey what ogres are like, and he's like, oh, they're like onions because they've got layers. Neural networks are like onions because they've got layers. So this is a diagram of a neural network, which you've probably all seen, and each of these circles is a perceptron. And it's the exact same way that a brain works. So I mentioned activation functions briefly earlier, but I kind of just glossed over them. They basically limit the answer to within a certain threshold. So you can make a classifier using these. A lot of neural networks these days you'll find actually use ReLUs, but it's important to note that in neural networks with loads of perceptrons, you don't have just one ReLU at the end. You have one after every perceptron, I believe, so you don't have like astronomical numbers coming out. It's essentially a classifier. Matrices. People were talking about matrices all the time, so at first I was like, okay, how do matrices fit into all this? Apparently they're actually just a really handy way of notating what happens within a neural network. I just have a little hand-drawn diagram of a neural network up there. There's actually a mistake in this drawing, my bad. The 5 and the 5 are equal, not 5 and the 1, and 3 and the 1 go over here, just to make sure that's clear. They're just a very handy way of notating what happens within the neural network. Okay, this is where I show the gap in my knowledge. TensorFlow is named after tensors, and I'll admit that I don't know the difference between a matrix and a tensor, a matrix and a tensor rather, because at first I tried watching some videos and they were all like, okay, matrices and tensors are entirely different, guys. Okay, so a matrix is an array of numbers and a tensor is an array of numbers. Do you see the difference? Not really. Okay, so I'm going to be honest, I have no idea. But Dad thinks that the difference between matrices and tensors is that people in tensors earn 30% more. So I'm just going to take forever. Okay. So where do we go from here? Anywhere you want, really. The world of AI now is just going absolutely insane. I mean, I'm actually particularly interested in music. I play piano a lot, and I love to get into music tech when I'm older. And there's a lot of different areas in artificial intelligence combined with music, such as TensorFlow's Magenta, which is like 10 neural networks in the arts. And there's also Iva Technologies, which is really, really interesting actually. They're a company based in Luxembourg who compose classical music for like movie scores and things like that. And it's actually really good using neural networks. And in fact, Iva is the first non-human composer to be recognized by copyright, which I think is pretty cool. But there are so many different things you can do. I mean, it's kind of unlimited, really. Another thing I'll admit, I don't know how regression works either. So we'll get on to the questions. Just don't ask about regression or tensors. Any questions?